You're driving down the highway at, I don't know, 70 miles an hour, and suddenly just dead silence.
Yeah, complete panic setting in.
Right. The engine didn't throw a rod, a timing belt didn't snap, and your oil pressure is totally fine. The car just experienced, well, brain death. The engine control unit, the ECU, has completely failed.
Which is becoming a massive problem as cars get more complex.
Exactly. So today we are taking an exclusive look into the highly specialized world of automotive digital surgery. We're going to explore what it actually takes to bring that dead computer back to life.
And, it's a process that requires a massive array of both digital and physical tools. This is stuff far beyond what you'd find in a standard repair bay.
Yeah, we've got a stack of really fascinating visual sources for this deep dive today.
Huh.
They're photographs taken straight from the workbench of an engineer at MVS Technical. For those of you who want to look up their work later, that's www.mbs-technical.co.uk.
Right, and they host a huge array of specialized equipment and diagnostic capabilities. They do complex ECU cloning and physical repair for the general public and for trade garages, too.
And looking through these sources from their workbench, you don't see wrenches or, hydraulic lifts. You see high-end diagnostic screens, raw circuit boards, microscopic soldering tools.
Yeah, and a complete labyrinth of wiring harnesses.
Okay, let's unpack this, because before we get into the physical wiring, we have to start with the actual brains of the operation. In these photos, the central command hubs are these rugged Dell laptops.
Mostly Dell Latitudes, from the looks of it.
Right, sitting right in the middle of a sea of metal boxes and adapters. But why are they using these older, heavy-duty machines instead of, a fast, modern Ultrabook?
Well, it really comes down to hardware stability and port availability. In high-level diagnostic environments, you don't want a fragile laptop that might crash because of a random background update.
Oh, right, like a forced restart.
Exactly. Or a laptop that requires a dozen flimsy USB-C dongles just to connect to the gear. These heavy-duty workhorses are designed to run specific, highly stable communication software for hours on end without any interruption.
Because an interruption could be bad.
Oh, an interruption or a crash during a data transfer can permanently brick an engine module. It's game over.
Wow. Okay, that makes the software running on these screens feel incredibly high stakes. On one of the Dell screens, you can actually see multiple overlapping windows reading flash memory in real time.
Right, with all the progress bars inching across.
And there's text that reads, checksum is calculated by the program. Now, I know checksums are important in general computing, but how does that actually protect the car's computer from being ruined?
So a checksum is essentially a complex mathematical algorithm used to verify data integrity. Think of it as a highly precise scale.
Okay, scale.
Right. When the engineer at MVS Technical pulls the operating data off a failing ECU, the software calculates the exact weight of that data.
Yeah.
Then, when they write that data onto a new donor ECU, the software weighs it again.
I see. So it's like a puzzle where all the pieces must add up to an exact predetermined mass.
Precisely.
If even a single grain of dust, or in this case, one corrupted byte of data, gets mixed in during the transfer, the scale tips.
Yep, and if those checksums don't match perfectly, the car security system will detect the discrepancy. It'll just outright refuse to start the engine.
Because it assumes someone tampered with it.
Exactly. It assumes the data is corrupted or compromised. The software on these laptops handles those complex calculations automatically, which ensures that the cloned data is a flawless mirror image of the original.
Which kind of brings up the interface itself.
Yeah.
I'm looking at a drop-down menu on the screen, and it is a massive list of acronyms. We've got all TDI Bosch, EDC17X UDS, Siemens PPD1.X K-line, FSI Bosch, MAD 9.1 CAN TP 2.0.
It's quite the alphabet soup.
It really is. What's fascinating here is the sheer volume of different systems listed. Why isn't there just like a universal language for all cars?
Well, basically because automotive manufacturers are fiercely protective of their intellectual property. They all design their control units completely differently.
So Bosch, Siemens, Delphi.
Continental, yeah. They each use proprietary architectures. And even within a single brand, the language changes from year to year.
Oh, wow. So an engineer at MVS Technical isn't just dealing with Volkswagen data or Nissan data. They're dealing with a dozen different dialects just within one manufacturer.
Exactly. To serve their diverse client base, which ranges from, the everyday driver to professional trade garages, their software must be capable of perfectly translating hundreds of unique systems.
So they might get a lockdown Audi module in the morning and a flooded Ford module in the afternoon.
And the engineer needs the software capability to communicate with both of them flawlessly.
But having the software is only half the battle, right? I mean, software is completely useless if you can't physically extract the data from a sealed metal box.
Very true, which naturally leads us from the laptops to the wild array of physical hardware bridges dominating this workbench.
Yeah, it's an extensive stack of specialized reading and writing hardware. Like on the bench, we see a bright orange and black tool called the foxflash.
Yeah, and next to it is a ribbed metal box labeled Kess Master Version.
Right, and a larger one labeled K-Tag Master Version.
I see those. But what do they actually do? If the laptop has the software, why does the engineer need 3 different master tools sitting between the laptop and the card's computer?
Well, those master units are the translators for the physical layer. The laptop speaks software, right? But the ECU communicates via electrical pulses over specific hardware protocols.
Oh, okay.
So tools like the K-Tag and foxflash, they manipulate voltages and signal timings to match exactly what that specific ECU is expecting to hear. They also manage the security protocols required to force the processor into boot mode, so they can read the raw memory.
Exactly.
And to do that, they are using a seriously complex physical network. I'm looking at a Kodiak breakout box and a Kodiak diagnostic cable, which looks like a heavy-duty connector that just splits out into multiple individual wires.
Yeah, breakout boxes like the Kodiak or Kodiak are essential for bench work. They allow the engineer to cleanly and safely route specific power, ground, and data signals to the correct pins on the ECU.
So it keeps everything organized.
Organized and safe. It prevents crossed wires and provides a safe, fused power supply to the module while it's being worked on outside the car.
Here's where it gets really interesting to me. In one of the photos, we have a clear view of an ABI D-Star tablet reading a Nissan Bosch EDC17C84 module.
Yeah, that's a great shot.
The tablet connects to an orange P003 plug adapter, but that adapter breaks out into this sprawling web of yellow wires, and the engineer has manually pinned each individual yellow wire directly into the tiny exposed metal terminals of the Bosch ECU unit.
It's a very delicate process.
It looks highly invasive. I mean, is this level of manual wiring really necessary just to copy data? When I go to the mechanic, they just plug a scanner under the dashboard.
Right, well, that port under your dashboard is the OBD2 port, and it's designed for basic diagnostics. It is essentially the front desk of the building.
Okay, the front desk.
The manufacturer leaves it accessible so mechanics can read standard emissions data and simple error codes. But the core memory, the fundamental operating system, that is locked inside a digital vault deep within the processor.
But wait, is it actually safe to bypass manufacturer locks like this? Doesn't forcing a connection with raw pins risk permanently frying the module you're trying to save?
It is entirely safe, but only if you have the specialized equipment and the precise knowledge of the hardware architecture.
Because if you guess wrong...
If you connect one of those yellow pins to the wrong terminal and apply 12 volts of power, yes, you will instantly short-circuit the board.
Yikes. So how do they safely get around that vault door?
By using what's called a bootloader. The bootloader is a tiny piece of code that runs right when the processor powers up, before the main operating system even loads.
What's its purpose?
Its job is to check for updates. So by pinning directly into specific microscopic test pads on the circuit board, the engineer can send a precise voltage signal to the processor right as it wakes up.
Oh. It tricks the processor into thinking it's back at the factory waiting for a programming update.
Exactly. It halts the normal startup process and just holds the vault door open. This allows the tools, like the K-Tag or ABI D-Star, to directly extract the raw data, like the flash memory and the EEPROM memory.
Bypassing the standard OBD2 security entirely.
Completely bypassing it.
So when they extract that raw data, what does it actually look like? It can't just be a neat English spreadsheet saying, fuel goes here, timing goes there.
Not even close. It looks like an absolute wall of numbers and letters. It's written in hexadecimal code.
Hexadecimal. Let's break that down for the listener, because I hear that term thrown around in computer science all the time. But
Yeah, it's pretty fundamental. So computers naturally process binary ones and zeros, but looking at millions of ones and zeros is impossible for a human to parse.
Right.
Hexadecimal is a base 16 number system. It uses the numbers 0 through 9 and the letters A through F. It condenses the long strings of binary into a much shorter readable format.
So instead of a massive string of ones and zeros taking up the whole screen, a specific instruction for the fuel injector might just read, like
Yeah.
1A4F.
Correct. When an engineer at MVS Technical is looking for a corrupted sector in the software, they are scrolling through thousands of lines of hexadecimal code looking for patterns that shouldn't be there.
Or isolating specific engine maps, I imagine.
Right, which requires a really deep understanding of software architecture.
Which perfectly illustrates why trade garages rely on specialized labs for this.
Yeah.
A standard mechanic isn't going to have a foxflash, a K-tag, an OBD star setup, and the Xcode knowledge to rebuild a bootloader file.
They simply don't have the time or the specific training. The automotive industry has become so compartmentalized that specialized ECU engineering is practically its own separate trade now.
We've spent a lot of time talking about software extraction and cloning. But if we connect this to the bigger picture, what if the trade garage or the customer doesn't want to clone the data to a new unit? What if they want their original unit repaired?
That's when we have to zoom in literally from the messy wiring harnesses to the microscopic level of physical circuit board repair.
Right, because the visual sources from the MVS technical workbench show a setup that looks like it belongs in a semiconductor manufacturing plant.
Yeah, they use a high-resolution digital microscope setup that feeds a live, highly magnified view to a monitor.
And through that screen, you can see an exposed green circuit board, revealing intricate details that are totally invisible to the naked eye. You see the tiny copper traces, which are, the physical highways the electricity travels on.
And you see surface-mounted resistors that look smaller than grains of sand.
Yeah, and these intricate silver solder joints holding everything down.
Plus, sitting beneath the microscope's ring light is the physical board itself. You can see components on there designed to handle much heavier electrical loads. Like, there are two large orange capacitors clearly labeled 100V 1500 UF.
Next to those tightly wound copper induction coils. But let me stop you there because the battery in a standard car is only 12 volts, right?
Mm-hmm.
Why would a car's computer need capacitors rated for 100 volts?
It's because of the fuel injectors. To force a modern high-pressure fuel injector open in a fraction of a millisecond, 12 volts just isn't nearly enough force.
Oh, okay.
You need a massive, instantaneous spike of voltage.
Ah, so those capacitors are acting like electrical slingshots. They pull in the 12 volts from the battery, store it up, and then dump a massive 100-volt spike directly into the fuel injector exactly when the processor tells them to.
That's a really great analogy. They store and release high energy continuously while the engine is running. But because they handle such high loads, they generate heat. And over time, they are susceptible to physical failure.
They wear out.
Yeah, they can swell, leak, or just blow entirely.
So what does this all mean for the engineer at the workbench?
Mm-hmm.
To me, looking at the fine tweezers lying next to the board under the microscope, it feels like we were watching someone prepare to perform microscopic cardiovascular surgery on a tiny electronic city.
It really does. And this raises an important question about the difference between a software engineer and a hardware technician.
How so?
Well, cloning an ECU is brilliant for data recovery, but a software transfer cannot fix a blown capacitor or a melted copper trace. If a massive power surge from a bad alternator brings out the physical pathway on the board, the K-tag tool is useless.
Right. The data has nowhere to go. So the engineer has to physically bridge the gap.
It's exactly.
They have to go in under the microscope, desolder the damaged components, clean the board, and place a new microscopic resistor or capacitor down, securing it with fresh liquid metal solder.
It requires an incredibly steady hand and an understanding of thermodynamics. You have to know how much heat you can apply to a specific sector of the board without accidentally desoldering the components right next to it.
It really highlights the dual nature of the operation at MVS Technical. To provide this level of service for both the public and for trade garages, you can't just be a mechanic.
No, not at all.
You have to be a software hacker who understands hexadecimal code, checks some algorithms, and bootloaders. And you have to be a microscopic hardware surgeon who understands voltage regulation, copper traces, and precision soldering.
The diagnosis dictates the required skill. Did water get into the housing and physically corrode the copper traces? Or did a battery drain cause a software corruption in the EEPROM memory?
Right.
The ability to diagnose the root cause and handle either scenario under one roof is what makes a specialized facility so critical.
When you step back and look at the comprehensive suite of capabilities we've explored today across this workbench, it is a seamless blend of code and copper. We started with the digital translation happening on those rugged Dell laptops, calculating complex checksums to ensure perfect data integrity.
Then we move through the intricate hardware bridges,
Right.
the Kodiak and Kodiak breakout boxes, the OBD SNAR tablets.
And the master tools forcing secure connections to extract data directly from the processor.
Right, and finally we zoomed all the way down to the microscopic solder repairs happening under the ring light of a digital microscope.
It really is a full spectrum of diagnostic and repair capabilities, serving everyone from the individual driver stranded on the highway to the professional trade garages trying to solve a puzzle for their own customers.
And none of that equipment functions without the specialized expertise to interpret the data and safely navigate the architecture of the modules.
So the next time you jump into your car, turn the key, the engine roars to life, take a moment to think about the highly programmed world living inside that sealed metal box under the hood.
It's doing a lot of heavy lifting.
It operates flawlessly, millions of times, firing fuel injectors with 100-volt spikes, calculating air mixtures in fractions of a second, and verifying its own security protocols. But when it finally fails, and your car experiences that brain death,
It is absolutely fascinating to know exactly the level of microscopic digital surgery it takes to bring it back from the dead.
it adds an entirely new dimension to how we understand the vehicles we rely on every day. You will certainly never look at a broken-down car or a rugged old laptop on a messy workbench the exact same way again.